calculate the shear stress in twisting at location X, which is up here, when we have a rectangular cross section that is mounted to a wall and we are applying torque of 700 Newton meters here at the end. We also must calculate the total angle of twist at the end of the beam. The shear modulus of this beam is 80 gigapascals. So let's write here the equation. Equation was T times length divided by Ix multiplied by G, like that. Then the value for stress, we need two equations for this one. So firstly, we must calculate the shear stress on the longer side, which will be tau. We will call this tau A. That is T torque divided by Wx, and then finally the tau at location X will be tau A multiplied by eta, like so. Also, we need the equation on how to calculate the section modulus. So section modulus is beta times height multiplied by b power to 2, and the second moment of inertia to calculate the twist is alpha times height times b power to 3. In this example, now the height, so the longer side of this rectangular cross section is 60 millimeters, and the shorter side B is 22 millimeters, like so. Well, now from this information we're capable of calculating first the ratio h divided by b. So h divided by b will be 2.7. And now with this information we can go to this table and find the values for alpha, beta and eta. Okay. Now we can see straight away that the ratio that we got is not exact values given on the table. Well, how do we estimate then the value which we need for alpha, beta and eta? Well, on this table I have drawn in here these values, and this is the change of value alpha when we go from 1 to 1.5 and from 1.5 to 2. And you can straight away see that these values, they don't behave linearly, which means that we cannot trust to we cannot just calculate that what would be the exact value with 2.7 ratio of 2.7. So we're just going to estimate it in this case. And how do we estimate it in this case? We do it so that we calculate the average of alpha from ratio of 2.5 and 3. We take the alpha so that we take alpha. In this case, we do it by taking 0.249 plus 0.263, and we take average from this one, and that will be 0.256. Beta, calculated in the exactly same way, will be 0.263, and finally the eta will be 0.76. Okay, now since we have the alpha, beta and eta, we can continue to calculate the shear stress and the twist. So shear stress on the side A will be torque divided by Wx, which will be 0. From here, which will be 0.263 multiplied by the height, which was 60 millimeters, so the longer side is 60 millimeters, multiplied by 22 power to 2 millimeters power to 2, and this will give us value of 91.7 megapascals. Then, using this equation and the eta value, we can calculate what will be the shear stress at location x. Tau x is eta times tau a, and that will be 0.76 multiplied by 91.7 megapascals, and this will give us value of 69.7 megapascals. And finally, we are going to calculate one more thing. We calculate the total twist. So delta gamma is torque multiplied by the length. The length in this case was 1000 millimeters. Divided by the I, x, which is the second moment of inertia. It's alpha times height times width power to 3. So the alpha is 0.256 times 60 millimeters times 22 power to 3 millimeters power to 3 multiplied by the shear modulus, which was 80 times 10 to power 3 Newton per millimeter squared, and this will give us a value of 0.0535 radians, and that is in degrees. It is roughly 3.07 degrees. So now we know what is the stress on the shorter side, shear stress on the shorter side, and we also know what is going to be the total twist at the end of that bar.